We begin with a set of three vectors in R3, as you see here. And these vectors just correspond to the columns of this matrix. So if you can read them a little better here, go ahead and read them here if you wish. But question is this an orthonormal basis? Well, ortho means orthogonal. Dot product of this with this, dot product of this with this, dot product of this with this are all 0. This is very easily verified. Write it out and you will see that it works out. Okay. The other question is the normal part. Okay. Are the magnitudes of these three vectors 1? Well, square root of 2 over 2 squared is 1/2, and add that to the square root of another square root of 2 over 2, which is to the square of the square root of 2 over 2 over 2, which is 1/2. And we get 1. And here we're going to get 1/6 and 4/6 and 1/6, which adds up to 1. Here we're going to get 1/3, 1/3, and 1/3, which adds to 1. So yes, these are all unit vectors. Again, you can easily verify that. So the answer to this is yes. Now, if we use this orthonormal set as a basis for R3, and if we assume that these are eigenvectors, okay, so we're going to assume that these are eigenvectors, then what does a linear transformation relative to this basis look like? Well, it's going to be a diagonal matrix where the eigenvalue of this matrix is on the first diagonal, or this vector, the eigenvalue of this vector on the second element, second row, second column, the second number down the diagonal, and the eigenvalue of this vector on the third. At this stage, we can make up any transformation we wish. We can pick any three eigenvalues we wish, and we can then get a linear transformation with these three orthonormal vectors as the basis. And to do that, and I'm not going to go through the complete explanation of this by waving my hands, we've been over this in detail. We put our three eigenvectors on the diagonal of a matrix, and that's going to be the transformation matrix relative to the eigenvector basis. That will have the effect, when multiplied by a vector relative to the eigenvector basis, of giving you a vector. When you substitute the first eigenvector, it'll give you double that eigenvector. Okay, so that makes it an eigenvector with eigenvalue 2. If we multiply this matrix by representation of the vector with respect to this basis, and if this vector happens to be our second eigenvector, we're going to get -3 times that eigenvector, for reasons that I don't have room to write out and don't want to say too much, but you ought to think about why that's the case. Hopefully you understand quite well why that's the case, because we've talked about it a good bit now. We want to represent that transformation relative to the standard basis. Again, for reasons you should understand very well, the column of eigenvectors matrix P, which is this one, this is our column of eigenvectors. Here's the eigenvector, 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 in the order of the eigenvalues that we put on the diagonal of our matrix, takes us from the representation relative to our orthonormal basis to the representation relative to our standard basis. So that if we want to develop the matrix A that takes us from the standard basis to the standard basis with these three vectors as eigenvectors, with the three eigenvalues that we have here, all we have to do is think about what happens if we start here. We're not sure what matrix to use here, but it's got to be equal to the matrix we get if we started here with some vector according to our standard basis, represented that vector relative to our eigenvector basis, then did the mapping in our eigenvector basis, and then took that result and represented it according to the standard basis. That means that this matrix A, which acts on this vector and takes us directly from here to here, should equal the matrix we get if we first multiply our vector by P inverse, and then by our diagonal matrix, and then by the P matrix, which is our column of eigenvectors matrix. That multiplication corresponds to, well, we start here. The first thing we do is we have to multiply by this inverse matrix. Now, I didn't mention, but it should be implicitly understood that an orthonormal basis, or rather an orthogonal matrix, which P is. Orthogonal matrix means that you have three column vectors that are orthonormal, orthogonal to one another, each one of magnitude 1. The inverse of this matrix, as we've seen elsewhere, is equal to the transpose of the matrix. So if we go from here to here, we're going in the direction opposite we need to go from the eigenvector basis to the standard basis. So we're doing the inverse of this matrix, and that's equal to the transpose. If we start here then, if we first multiply by the transpose, which takes us from here to here, and then we multiply by the diagonal matrix, and then we multiply by the column of eigenvectors matrix, the P matrix, we should get the A matrix. Well, we do that. Now, I've just written out the product. We didn't actually calculate it in class. You know you can verify it. I know you can verify it. And if you have time, do verify it, but it does work. Okay, so what we get when we do this turns out to be a symmetric matrix. This is the matrix we get. 5, 6, 4 thirds, 7, 6. Well, it's on your paper. You can look at it. And we note that these two elements are the same, these two are the same, these two are the same, so that the rows of this matrix are equal to the corresponding columns. The first column is equal to the first row. The second column is equal to the second row. The third column is equal to the third row. So this is symmetric. Now we'll prove, and you see a little bit of the proof over here, we'll prove that that's always the case. That we always get a symmetric matrix if we do this. And the only condition we need is that P transpose be the inverse of P. So we'll prove that, but it did work out this time, so it validates. Now this is part of an if and only if statement, which says that this matrix, if this matrix is symmetric, then we get three orthogonal eigenvalues that we can normalize to get an orthonormal set. So that we can orthogonally diagonalize our matrix. And that's kind of a big deal. We'll talk a little bit more about why that's true. I talked about it in class. Let's stay on track here, okay? And similarly, if we start with three eigenvectors, three orthonormal vectors in R3 in this case, and do what we just did here, multiply any diagonal matrix by the transpose matrix and the diagonal matrix in the original matrix, where the eigenvalues are on the diagonal matrix, we will get a symmetric matrix. Let's stop for just a minute and understand that I can generate an unlimited number of problems, an unlimited number of symmetric matrices, just by picking different eigenvalues to put on the diagonal here. Okay? And any matrix that I get will represent a transformation having these three eigenvectors with the corresponding eigenvalues. Okay. Well, we're going to go on with this, and what we're going to do now is we're going to pretend we never saw this process. We're just going to say, okay, here's our symmetric matrix. Let's find the eigenvalues and the eigenvectors and see if we can find an orthonormal basis. We'll do that in the next clip.